Hi, my name is Jessica Strickland. I'm from the University of Twente. I'm not there right now. Um, I'm going to be talking about flow blockage in a neutral atmospheric boundary layer using large eddy simulations. So the blockage that I'm going to be talking about are wind turbines, which you can probably tell by this delightful doodle down in the corner. I won't talk much about large eddy simulations. I'm sure there's a lot of talks out there that might include it. So let's continue. If I can figure out how to get to the next slide. There we go. So what is flow blockage? Well, one might like to assume that when a turbine receives wind, that it is undisturbed. Well, this is not necessarily the case. Incoming airflow can actually be influenced by the upcoming obstruction. And this has been shown, and this theory presented by Mendici et al. Is basically the center line velocity preceding a wind turbine divided by the infinite value. So if you were really, really far upstream where it should be undisturbed, well, you would kind of like to assume that this would be equal to 1 until it hits the turbine. But this is not the case. As you can see here, if I plot this, there's actually a deficit preceding the turbine. However, there are other interesting features as well, because as this affected wind comes in and either goes through the turbine or around the turbine, how is this going to influence a close neighbor? How are they going to influence each other? And also you have downstream turbines, which are also influencing the upstream flow. So that's what we care about. That's what we're going to look at. So in general, as you said, it would be nice to assume that each of these in this row performs the same as a single turbine because it's receiving wind that has not hit anything yet. But that's not necessarily the case. And there are a few studies that have looked at this, but we use large eddy simulations so that we can do large scale wind farms and provide more realistic inflow conditions and do an encompassing number of cases. So I'll look at a single turbine as a reference, an infinite row of turbines, and an entire wind farm, which also has infinite rows and 8 of those infinite rows. So the variable of interest is actually, well, spacing, but you have span-wise spacing and stream-wise spacing of turbines. So how close they are, because blockage should be enhanced if they're closer together. You may see spacing as tiny s, which means that it's dimensionless, and I've divided by the diameter, which is 100 meters in our case. So to begin, to kind of go back to that induction idea, if I compare the induction of a single turbine to the average induction in front of a turbine in each turbine in a row, so we take the center line, the velocity along this line, and normalize it by the really far upstream value, well, we get this result. And what I'd like to point out is that the velocity deficit is more pronounced for the rows than the standalone turbine and is also farther reaching. So it goes, this less than 1 value exists farther upstream. And as well as spacing decreases, so for example, the blue case, which is the smallest, the induction is enhanced, which makes sense. So the variable of interest generally is the performance of a wind farm. And typically a company would know or have expectations for the performance of a single turbine. However, we're going to show that it is not necessarily the same if you put them together in a row. So the average power of a turbine in this row compared to this single turbine is as follows. It is notably above 1 for all points, so close span-wise neighbors seem to benefit each other here. As well, when the spacing is smaller, this blockage, this effect is more enhanced, and when it's larger, it's actually approaching 1, which means that a turbine here performs similarly as a single turbine. And as well, the results are not significantly dependent on the roughness scale. So this reflects whether we're doing onshore or offshore or onshore conditions, and the red and blue don't differ that much, and they match fairly well with other experiments or numerical studies. However, typically these turbines are put into an entire wind farm, so we'll compare the front row of a wind farm, which is where we expect to see this impact of blockage the most because, well, again, ideally, one would use this as a normalized, use the front row as a reference because it's receiving undisturbed flow. Well, when compared to a single turbine, again, we see this is not the case. However, here it's a bit more complicated. When the streamwise spacing is small, we see kind of a similar shape or behavior as last time. Sorry, when the streamwise spacing is larger. But when the streamwise spacing is small, like Sx equals 1.96, you actually get values lower than 1, which means that close downstream turbines actually hinder the performance of the first row. So if we take the same data and we plot it for the mean geometrical spacing, as shown here, so to kind of look at it more in terms of turbine density, as opposed to just Sx and Sy separately, the data doesn't collapse, unfortunately, which highlights the competing effects of streamwise and spanwise blockage in that it makes the global blockage effect layout dependent. So when compared to a single turbine anyway, when you look at these two configurations, even though the mean spacing of the turbines is the same, the actual layout is different, and this affects the amount of blockage that is observed. So when we kind of like to isolate that downstream blockage effect, so we also compare the first row of a wind farm to just the solitary infinite row. So that way it really is just the adding of turbines behind it. And when doing so, we see that all values are below 1. So again, we see that hindrance and only the hindrance of the downstream turbine. So the spanwise blockage is effectively normalized out. And again, the blockage is negligible at larger spacing. So it's most prominent when the mean geometrical spacing is small. Also, I would like to highlight that this dashed line we show here is actually from the wind tunnel experiments done by Segalini et al., which match fairly well with what we produced. And so if you're going to take anything away from this, I mean, maybe you even skip to this part, I would like to highlight that laterally closely spaced turbines apparently can benefit each other. For our particular setup with infinite rows, and the close downstream turbines actually hinder the performance of the first row. The first row of a wind farm isn't necessarily a perfect reference. As well, global blockage is layout dependent, so the actual streamwise and spanwise spacing of that layout matter. And this effect, the blockage in general, will be enhanced as the spacing decreases. So the closer the turbines are together, the more of an obstruction it is. And the observed flow blockage, though very dependent on turbine spacing, did not appear to be dependent on the surface roughness, which is also considered the turbulence intensity at hub height. So thanks for listening.